Hello viewers, in today's session we are going to discuss another important problem from definite integrals, and in this session we are going to discuss this definite integral where we have the limits from 1 to 2 and the integrand is x square plus 1 divided by x raised to 4 minus x square plus 1, and here we have dx, right? So viewers, we have already discussed these kind of integrals in our earlier videos, and we have discussed the form that is integral of this type, that is x square plus 1 over x raised to 4 plus lambda x square plus 1 dx, where this lambda belongs to the set of real numbers, right? So we have discussed how to solve these kind of indefinite integrals where the integrand is of this form, where the numerator is a quadratic function and the denominator is a biquadratic function, right? So here I will make use of this method to solve this integral. So now let us call this integral as I, right? So here we have the definite integral, and here we have the indefinite integral, right? So if we compare the integrands, then we can easily see that here we have minus x square. So the value of lambda is equal to minus 1, right? So to solve these kind of integrals, what we do, we divide the numerator and denominator by x square. So the first step in solving these type of integrals is to divide the numerator and denominator by x square. So here we can now write x raised to 4 minus x square plus 1 over x square, and here we have dx. So now we can write 1 to 2, and here x square plus 1 over x square can be written as simply 1 plus 1 over x square, and here we have dx, and in the denominator we can write x square in the denominator of these three terms. So we have here x square, then we have minus 1, and then we have 1 over x square. Now we can collect these two terms. So our integral becomes 1 to 2, and here we have 1 plus 1 over x square dx, and in the denominator we have x square plus 1 over x square, and here we have minus 1. So the first step is to divide the numerator and denominator by x square, and now the second step is to make use of the method of substitution, and in the denominator we have 1 plus 1 over x square dx. So what we will do, we'll assume this substitution, that is u is equal to x minus 1 over x, right? So when we differentiate u with respect to x, we can write du over dx, and here the derivative of x is 1, and here the derivative of 1 over x is minus 1 over x square. So here we have 1, and this minus when multiplied together it becomes positive, then here we have 1 over x square. So now we can write du is equal to 1 plus 1 over x square, and here we have dx, right? So now we can easily replace the numerator by du, right? Okay, now let us change the limits, and here x varies from 1 to 2. So when x is equal to 1, then the value of u is given by 1 minus 1 over 1, that is equal to 0. And when x is equal to 2, then u is 2 minus 1 over 2, that is 4 minus 1 over 2, that is 3 by 2, right? So when x varies from 1 to 2, u varies from 0 to 3 by 2. So now here we have changed the limits, and now let us take care of this denominator. Now in the denominator we have x square plus 1 over x square, right? So what we will do, will make the square of both sides in this substitution. So we have u square, and here we have x minus 1 over x square, and taking the help of a minus b whole square, we can write x square minus 2 times x times 1 over x, that is 2ab, and here we have b square, that is 1 over x square. Now here this x and this x get cancelled, so we have x square minus 2 plus 1 over x square. Now we can take this negative 2 to the left hand side. So we can now write u square plus 2 is equal to x square plus 1 over x square, right? So now we have expressed x square plus 1 over x square in terms of u, that is u square plus 2. So now we can rewrite this integral, that is I, in terms of u. So we can now write the limits are from 0 to 3 by 2, and in the numerator we have du, and in the denominator this term is equal to u square plus 2, and here we have minus 1. So we can now write 0 to 3 by 2, and here we have du over u square plus 1. 2 minus 1 is 1. Now here 1 can also be written as 1 square. So now this is a standard integral, that is we can make use of this result, that is integral dx over x square plus 1 is given by tan inverse x, right? So here we have the variable u du over u square plus 1 square. Here we can write this one as 1 square. So we can now write I is equal to tan inverse of u, and the limits of integration are from 0 to 3 by 2. Now substituting the limits and taking the difference, we have tan inverse 3 by 2 minus tan inverse 0, and this is tan inverse 3 by 2 minus 0, because tan inverse 0 is 0. So now we can write I is equal to tan inverse 3 by 2, right? So now the value of this integral I is equal to tan inverse 3 over 2. Hello viewers, in today's session we are going to discuss another important problem from definite integrals, and in this session we are going to discuss this definite integral where we have the limits from 0 to 3, and our integrand is square root of x cube divided by 3 minus x, right? So here we are going to solve this definite integral with the help of beta and gamma functions, right? So let us start, and let us first call this integral as I, right? So in order to solve this integral, let us first take the help of the method of substitution. So let us substitute here x is equal to 3t, right? So here we are introducing the variable t such that x is equal to 3 times of t. So dx over dt is now equal to simply 3, because the derivative of t with respect to t is 1. So we can now write dx is equal to 3 times dt. And now here the limits of integration vary from 0 to 3. So when x is equal to 0, then 3t is equal to 0, and this implies t is equal to 0. And when x is equal to 3, then 3t is equal to 3. So t is equal to 3 over 3, that is equal to 1. So when x varies from 0 to 3, then t varies from 0 to 1. So let us now express this integral I in terms of t. So here we have 0 to 1, and x cube is equal to 3t cube, and in the denominator we have 3 minus 3t, and here we have the exponent, that is 1 over 2, and dx is equal to 3 dt. So now we can write 0 to 1, and here 3 cube is 27, and this is t cube, and in the denominator we can take 3 common, so we have 1 minus t, and here we have the power, that is half, and here we have 3 dt. Now here we can cancel this 27 with 3, so this is 3 times 9, and we can now write 0 to 1 9t cube divided by 1 minus t, and here we have half, and this is 3 dt. Now the square root of 9 is given by simply 3, and t cube raised to half is given by t raised to 3 by 2, and in the denominator we have 1 minus t raised to half, and here we have 3 dt. Now 3 times 3 is 9, so we can take this 9 outside the integral, and here we have 0 to 1 t raised to 3 by 2, and we can take this term to the numerator, and we have 1 minus t raised to minus half, and here we have dt. So now this integral I can now be written as here we have 9, then we have 0 to 1, and t raised to 3 by 2 can be written as t raised to 5 by 2 minus 1, because 5 by 2 minus 1 is equal to 3 over 2, and here we can now write 1 minus t raised to half minus 1, because half minus 1 is equal to minus half, and here we have dt. So now this integral is similar to the beta function, that is beta m comma n is defined as the integral 0 to 1, we have t raised to m minus 1, and here we have 1 minus t raised to n minus 1, and here we have dt, right? So for the positive numbers, that is m and n are greater than 0, the beta function, which is also known as Euler's first integral, is given by 0 to 1 t raised to m minus 1 1 minus t raised to n minus 1 dt, right? So this integral is similar to this one, and if we compare these two integrals, then we can easily find that m is given by 5 by 2, and n is given by half, right? So we can now write I is equal to 9 times the beta function, that is beta of 5 by 2 comma, here we have half. So now to calculate the value of this beta function, we can make use of the relation between beta function and gamma function. So beta m comma n is given by gamma m times gamma n divided by gamma of m plus n. So now this expression is now 9 times gamma of 5 by 2, then we have gamma of half, and in the denominator we have gamma of 5 by 2 plus half, right? So now we can write 9, and here gamma of 5 by 2 can be written as 3 by 2 times half times gamma of half, because we know that gamma n plus 1 is given by n times gamma of n, right? So when we take n is equal to 3 by 2, then here we have gamma of 3 by 2 plus 1, and here we have 3 by 2 and gamma of 3 by 2. So this is gamma of 5 by 2, and here we have 3 by 2. Gamma 3 by 2 can also be written as half plus 1. So again, applying this rule to gamma half plus 1, we can write 3 by 2. Then we have half, that is n times gamma n. So here we have gamma half, right? And gamma half is equal to square root of pi. So here we have 3 by 2 times half times square root of pi. So this is 3 by 4 times square root of pi. So here gamma 5 by 2 is now equal to 3 by 4 times square root of pi, and here gamma half is square root of pi, and in the denominator we have 5 plus 1 6, 6 over 2 is 3. So gamma 3 is given by 2 factorial, because we know that gamma n plus 1 is equal to n factorial, right? So gamma 3 can be written as gamma 2 plus 1. So here n is 2. So we have 2 factorial, that is simply 2. So here we have 2. So now we can simplify this expression. This is 9 times 3, that is 27. And here 4 times 2 is 8. And square root of pi times square root of pi is simply pi. So the value of this integral I is given by 27 pi divided by 8. So viewers, this is how by the application of beta and gamma functions we can easily evaluate these kind of integrals.